Hi everyone, I'm Winnie Charles Inchi of Group 24, and today we are presenting on the root locus analysis of a unity feedback system. So our goal is to sketch the root locus for k, which ranges from 0 to infinity, and find the value of k for which the system becomes unstable, and also determine the frequency of oscillation at that value of k. My group members will handle the presentation from here going.
Hello everyone, my name is Bosomtreya Kosia Sewa Mami, and today our task is to sketch the root locus, find k that causes instability, and find the oscillation frequency. So to construct the root locus, the first step is identifying the poles and the zeros. The poles are obtained by settling the denominator to 0. So for this given function, we get s1 to be 0, s2 to be negative 2, s3 to be negative 3 plus 4j, and s4 to be minus 3 minus 4j. This means that there are no finite zeros. That is, the total poles are 4 and the total zeros are 0. The root locus always starts at the poles when 4 is equal to 0 and then moves towards 0 as k approaches infinity. Since there are no zeros, all branches go to infinity.
My name is Oliver, and I'll tell you how the importance of the poles, or why the poles matter. So the poles generally tells us how the system behaves. So for example, when the poles are on the left hand side of the plane, it shows that the system is stable. When on the right hand side of the plane, it shows that the system is unstable. And when the poles lie on the imaginary axis, it states that the system states where the system oscillates. So generally, the main purpose of the poles is to tell us where the root locus begins. It tells us the number of branches, and it tells us where the system oscillates. So with the understanding that we have now, we can move on to determine where the root locus exists on the real axis.
My name is Oliver Kwame Amankwa-Adai, and I'm here to help us determine where we can find the real locus in the real root locus line. The rule we are using over here is that we are using the real axis root locus. And one thing we are supposed to note in this rule is that we don't need the complex poles in this rule. So from the graph we have on the slide, we can easily tell that our root locus lies between 0 to minus 2, as you can all see. This tells us that our root locus exists to the left of the odd number of row, poles, and zeros. Thank you.
Hello, my name is Gideon. I'll be continuing from where my colleague left, and I'll be explaining asymptotics, that is, from the direction to infinity. So in this section, since all branches go to infinity, we calculate and go to know their direction. And since all direction goes to infinity, we need asymptotic angles and centroid to determine how the system goes. So for the centroid, so is the sum of poles minus sum of zeros divided by p minus z. And so for the calculation, it will be equal to 0 minus 2 minus 3 divided by 4, which is equal to minus 2. So the angle formula for this will be equal to 2k plus 1 times 180 degrees divided by p minus z, and it will become k is equal to 0, 1, 2, 3. So this means this as is all radiated from the point x, which is equal to negative 2 on the real axis. The angle which is 45 degrees to 315 degrees are symmetrically placed at 90 degrees intervals. Thank you.
Hi, my name is Musa Mohammed, and I'll be taking you through the breakaway point. Talking about the breakaway point is where the root locus branches leave the real axis and enter the complex plane. This occurs between the real poles at 0 and negative 2. To find it, we differentiate k with respect to s and set it to 0. So this gives us the equation 4s cubed plus 24x squared plus 74x plus 50, which is equal to 0. Solving this, we get s is approximately negative 0.898. This lies within the valid region negative 2 0. So it is the actual breakaway point.
Hi everyone, my name is Eboasi. So I'm taking a look at how to determine the stability using the Roth-Hurwitz criteria. So first of all, we form the characteristic equation of the closed loop system, which is given as s exponential 4 plus 8s exponential 2 plus 37s exponential 2 plus 50s plus 25k is equated to 0. Then we construct a rod array, which is illustrated over there. So for the condition, it states that for a system to be stable, all elements in the first column must be positive.
Hello everyone, my name is Fahad Aruna and I'll be taking you guys through slide 8. So from the root array, we observe that one term becomes 0 at a certain value of k. This value is the critical gain, where the system transitions from stable to unstable. After solving, we obtain that k now becomes critical, approximately 9.65. And now, system which is stable when k is less than 9.65. And then now, when the system is unstable, k now becomes greater than 9.65. Thank you very much.
That's to negative g, 4g, and then they travel to infinity. We can also see that the real axis locus exists only on negative 2, less than s less than. So from there, we also see that the frequency of oscillation at the instabilities stability omega is equal to 2.5 rats per second, and then the system crosses into instability at k critical 9.65. So this is the end of our video. Thank you for watching. Bye.